Hi everyone. Let us now start our Gate CSE AIMT2 solution. So this is AIMT2. So let's start the solution. And I will be discussing my subjects and Deepak sir will be discussing his subject. So first let me tell you that in AIMT2 Gate Computer Science, there has been 4,033 students have appeared live, which means that like actually this number is so big that at least I have not seen this number in any platform, in any other coaching or anywhere live for Gate Computer Science in any test. Okay, so this number is significant number. So, like, I just want to thank you, all of you who have appeared, who have trusted in Go classes, and who have spent 3 hours at this crucial time. Because your trust automatically bring motivation to us. Because if you're trusting, then we are obviously more motivated to put more efforts. Okay. Now let's just start this question. So this question has been asked in AMT2, and this question is related to Banker's algorithm deadlock, right? Operating systems question. So before I move to this question completely, and before I solve this, with the detailed analysis, first let me tell you what is this Banker's algorithm very quickly. So basically, uh, I mean, obviously I cannot tell you in this particular session, I cannot tell you from very scratch. I'm just assuming that you know bit of this, and then I can tell you bit more about it. Okay. So Banker's algorithm. So how does this algorithm work? Let me just show you. See, suppose there is some state of the processes, which means let's suppose some processes, let's suppose P1, P2, P3, there are some processes, they are currently holding, okay? They're currently holding. So this number I'm writing, which is currently holding some resources. Let's suppose this is holding three resources. This is holding two resources. This is holding, let's suppose, three resources and so on, okay? So this particular number or these particular numbers are basically currently holding. Okay, these many resources, these processes are holding. Now suppose one of this process or maybe some new process, let's suppose one of this process or some new process, maybe P4, or maybe one of this process could be, let's suppose, P2. See, this is, let's suppose, at some time t equal to 5, or let me take t equal to 0. I mean, let's just start with this time t equal to 0. And suppose P2 at some point in time, maybe t equal to 10. Okay, t equal to 10, P2 says that I want two more, something like this, right? P2 says that I want two more, right? In that case, will this request be granted or will this request be denied? It is actually checked by Banker's algorithm. So how does this algorithm work? Is basically, it says that, see, currently these are the currently hold of the processes of the resources. Then it says that, let me just do one thing. Let me just assume, okay, let me just assume that P2, since P2 wants two more, let me just assume that we are giving these two more, which means if you give these two more, it will be four, right? Okay, just to not get confused with this four, let me take some other number here. Let me take six here, okay, or maybe five here, six here. Okay, I mean, this four and this four are different. So yeah, so basically what I'm saying that, see, Banker's algorithm will decide whether to give these two more or not, right? This is the whole job. Now, will this give two more or not? It is basically done by certain process. How? It first pretend means, like, in the algorithm, it actually, it's just a variable. For the algorithm, it's just a variable until unless you actually give it. Okay, so algorithm works like this, that it pretends, kind of pretends means like change the variable. Okay, which is, I mean, from this 2 it will update that to 4. Okay, so kind of pretend, not actually giving, just algorithm is running. Okay, pretends that give two more, I mean, whatever is required, right? Give two more. And then if that is done, I mean, if you give two more, then what will happen? That is basically calculated, which means that if this is the current state, okay, if you pretend that, okay, you are giving two more, then this will be the current state. And if this is the current state, in that case, is this state is safe state or not? That's what Wenger's algorithm also check. So basically, now it checks, you can say, now, I mean, the next step is that now it checks whether the given, now the I mean, this state is basically the safe state or not, right? So now the algorithm, checks if the given state is safe state or not. Okay. So I hope you're getting the process. Like we are starting with some state 623. I mean, this is the currently hold, right? And then at some point in time, this is like dynamic asking, right? I mean, P2 is dynamically, or maybe any other process is dynamically asking for some resources. So it's like you can say it is like dynamic asking, right? Dynamic means like I mean in the continuous time frame. I mean it can ask for anything, like we don't know whether it is 2 or maybe it is 3. I mean obviously it will be based on whatever the process has already promised as maximum need. So there is something called maximum need, that is that process already promised before starting the execution, okay, according to the Banker's algorithm. I mean Banker's algorithm actually need it, okay. So yeah, basically this is a dynamic checking. So which means that at t equal to 10, it is asking for some resources. Then if you give some resources, then it first pretend that okay you give, and then after that if it is in safe state or not, okay, it will check whether it is safe state or not. Now suppose the check is succeeded, which means let's suppose that after this check you get to know that actually this is in safe state, okay. I mean the system will go to the safe state. Then then instead of just pretending, you actually give, okay. In this case, instead of just pretending, you actually, you means the Banker's algorithm or the operating system, whatever you like to call, okay, you actually give those two more, right? Suppose, obviously, that could be the case that it is resulting into unsafe state, right? It is resulting into unsafe state. In that case, what will happen? In that case, process the resources will not be given. The reason I will just tell you. So basically, in this case, those two more will not be given. So you can say request declined. Okay, so request declined. And here the request is granted, okay, request granted here. The reason is that, see, this is very simple algorithm, it is not very complicated. The thing is that it will, see, we always want to win the safe state. I will just tell you why unsafe state is a problem, okay. I will just tell you in a while. But we always want to win the safe state. So if you give it, then after giving it, are you going to the safe state or not? This is the main question that you ask always, okay. If you're going to the safe state, then there is no problem, okay. If you're going to unsafe state, then request will be declined. It is like called pessimistic kind of approach, which means unsafe state doesn't mean deadlock, but still it's unsafe, like there is a chance of deadlock, okay. So here I'm not saying that giving those two will give you the deadlock. There is a chance of deadlock, so that's why I don't want to even take that chance, okay. Don't worry about this unsafe state. I will just tell you, I mean, in bit more detail after solving the question. But the layout is like this, right? Okay. So this will be more clear. Let me first solve this question, and then I will be clearing this unsafe state also. So the question says that you have currently these, I mean, this is a screenshot, or this is like a snapshot of the system where the two more numbers are given to you. That 150 is basically the total number of resources that you have. And P4 is entering with the maximum requirement of 60, which means, see, I already have this. Now P4 wants to again enter with the maximum requirement of something which is given as 60. Okay. So this number is given as maximum requirement is 60. Okay. This number is given as 60. Now currently obviously it holds 0. I mean there is no, before has just entered. Okay. So there is no current holds. And then they are saying the total resources that you already have, total resources are 150. Now in this question they're asking that in the options, let me just tell you what they're asking. They're asking that if you give, okay, if see, so there is a difference between maximum need and what process is currently needing or currently want, okay. See, in total, in maximum, it is actually, it will require 60, okay. Maximum at most it will require 60. But at present, at t equal to 0, t equal to 5, or wherever, okay, no, I mean at present basically it is asking, it may not ask for 60, so it is asking for, let's suppose, 25, okay. So you can say now process is demanding 25, right? Now if you give those 25, which means if you write 25 here, if the process is now currently actually holding 25 or something like this, okay, whether writing, I mean, if you give those 25, then in that case, will you go to the safe state or not? That's what I want to check. See, that's very simple. Let me just tell you that you have total resources this, and already you are allocating, I mean, already currently holds, like you can say the available resources, right? I mean, the available, let me write, available are 150 minus 45 plus 40 plus 15. So 45 plus 15 is 60 and plus 40 is 100. So available are 50 with you. So the interesting thing is that 50 are available with you, and now some process is getting entered, and now that process is asking for 25. Okay, so it is wise to give 25 or not? That's what we want to check. The question is very simple. So what you can do, you can first, calculate what is the future need. I mean, basically the currently hold is okay, but let's just also calculate the future need, because see, you have, let's suppose you have 50 rupees and someone is asking 25. Okay, someone is suddenly asking 25 to you. You will give 25 or not, it will depend on your future planning, right? Obviously, so operating system will need to plan future, so that's why it has to check the all the process future needs, right? So that's why this future need is important. Okay, so this future need, now let me draw the horizontal lines. Okay, okay. So basically, let's suppose I'm writing the number here. So basically, the future need will be 70 minus 45. 70 minus 40 is 30, so it will be, I think, 25. 60 minus 40 is 20. 60 minus 15 is 45, right? Okay. So these are the future needs, right? Now some process is asking that I want 25, like currently you have 50, and then some process is asking I want 25 more, right? So if you give 25, then future need will be here 35, right? Okay. See, in that case, see, these are the available, but if you give 25, right? If you give 25, then what will the available after P4? You can say, let me write something like this, available after P4, right? After P4, how many will be available? So 50 are already available with you, but if you give 25 to P4, then you will be having 25, right? You will be having 25. Now, with this 25, you need to plan everything. With this 25, can you plan these future needs? Okay, with this 25, your job is to see can you plan these future needs. So if you have 25 with you, and if you can plan these future needs, then you are in the safe state. If you can't plan these future needs, then you are not in the safe state. It is as simple as that, right? So if you have 25 with you and the future needs are like this, then obviously you can satisfy this future need. You can also satisfy this future need. So you can satisfy at least two, right? I mean, so basically the moment you satisfy P1, you can also satisfy basically P2. So P1, P2 you can anyway satisfy. But the moment you satisfy P1, the interesting thing is that the moment you satisfy P1, whatever P1 is currently holding, which is 45, right? And whatever, like, the moment you satisfy this P2, whatever P2 is currently holding, which is 40, they will also release. I mean, see, once you see, the thing is like this, you have 25 with you, give all those 25 to P1, and P1 will take some time, but it will eventually finish, right? But the moment P1 is finishing, it will obviously release this 25, which is okay, and it will also release whatever it is currently holding, right? So with this 25, you can finish P1 execution, and P1 will release these 45 also. So basically, after P1 release, you will be getting 25 you already have, right? 25 you already have, but after P1 release, you will be getting 45 from P1, and then these are the total available with you. And with this available, I think you can satisfy any of this need, right? I mean, once you satisfy P2 need, P2 will also release 40. Once you satisfy P3 need, P3 will also release 15, right? I think you can satisfy everyone's need, right? And once you satisfy, I mean, this need, it will also release 25. So basically, you can have P1, P2, P3, P4 as one of the safe sequence, right? I mean, this is called safe sequence, because in this sequence you can execute everything. So if you have 25 with you at this moment, and this is the future need, then obviously you can satisfy, I mean, you can execute P1 first completely, then P2 completely, then P2, P3 completely, then P4 completely, right? This is interesting question. So I hope you understood this. Now in other options, so basically this was MSQ question. So they are asking whether like 25 will lead to the safe or unsafe. So B is the correct answer. But let's just see other options. In other options, basically they are saying, let's suppose P4 is requesting 35 instead of 25. There P4 is requesting 35. Okay, so P4 is requesting 35. Let's suppose, which means let me here. So instead of 25, so this is the currently available with you. Now P4 is coming. Like this is the same picture that we have. But for P4, it is, let's suppose here it is requesting 35, right? 35. Then future need will be 25. In that case, sorry, future need will be, yeah, 25. So yeah, P4 is requesting for 35. Let me just check. So basically here you have 70 minus 45, 25. 60 minutes, that's fine. Okay. Yeah. So I think everything is fine, right? So basically, I was just cross checking if everything is fine. So now available will become how much? Since you are giving the 35, after giving 35, you will be having 15, right? Available will be 15. Now with this 15, can you satisfy the future needs? Since you cannot satisfy any one of the future need, so obviously this is not a good idea to give 35, right? Because in future, what if P1 directly asks for 25, P2 is asking for 20, and I mean there's a possibility that there is like I mean the system will go to deadlock. Why? Because you are not able to satisfy anyone's future need. So that's why this is called unsafe state. Okay, so this is called unsafe. I will just tell you in a minute about it more. So but here what I'm telling you is this, that if you have available which is lesser than anyone's future need, I mean you are not able to satisfy anyone's future need, then this is called unsafe state. And then if P4 is requesting for 35, then system will go to unsafe state. Okay, so basically if P4 is requesting 35, then system safe, because no, P4 requesting system safe, no. So basically only B is true because in P4, both of the options are talking about the safe state, right? So that's why only B is true. So let's just see the answer. Yeah, answer is B. Great. But now let's just talk a bit more about the unsafe state as I promised to you, right? So let's just take this scene only, this example only, to explain the unsafe state little more. Okay. So suppose you have this screenshot or this a snapshot with you of the system. Okay, and then you are having available only 15. As we know that this 15 is lesser than anyone's future need, so this is unsafe state. But what does this unsafe state really mean? Okay, we need to understand that. See, is this a deadlock? First tell me, is this a deadlock? Is this a deadlock? Think about it. See, you have total available with you. Let me make this question very simple. Okay, instead of giving you so much of information, let me just make this question very simple to you. um, okay, let me just trim this question and remove the information which is not needed to solve this question. Okay, the question is simple, but still. Okay, suppose this is the question where I am giving you the future needs of some processes. Okay, okay, because to check unsafe state you just need two information. One is I mean whatever is the available currently available with you, and one is the future needs. Okay, I mean obviously like you also be needing for, but for this purpose of this question, like this is fine. But obviously you also be needing like currently hold, if that future need is basically I mean if one of the future needs is getting satisfied, but after satisfying there is no other future need is getting satisfied. So in that case you also need the whatever this process is currently holding. But for this purpose of the question, I think this information is enough. So tell me, can you satisfy anyone's future need? So answer is no. So is this system in deadlock? Just forget about this question. Like, suppose we are not solving this question, okay? We are not solving this question. Suppose that this question is done, I mean, we are not worrying about this question. We have solved this question, we have found the answer is B, and then let's just move on, okay? Now we are discussing some concept which is basically not dependent on this question, okay? So let's just suppose that we just want to understand one concept of unsafe state, that what is this unsafe state and what is this deadlock. Okay. Suppose we want to just understand this concept of unsafe state. Tell me, is this a deadlock? Then answer is maybe or may not be. I mean, currently the deadlock is not guaranteed. It's just called unsafe state, which means we are not safe. Now, who will determine whether it is a deadlock or not? It will depend on the actual need. You see, something called future need and something called really they are needing or not. Which means in future at most the process might need 25, but is it really needing 25, and that too at the same time? Which means let's suppose in future actual need, okay, actual need of, let's suppose, P1 comes out to be just 10 processes, okay. Let's suppose in that case, see, P1, let's suppose, currently holding how much? 45, okay. So it is currently holding 45, right? So P1 actual need at t equal to some time, it actually, let's suppose, 10. And then obviously you can grant that, I mean, you can basically, since the available are there, and let's suppose you're granting and everything is fine, okay, you can grant it, right? And then after that, after some point in time, P1 finishes the execution, finishes, right? And then obviously once P1 finishes, P1 will release whatever it is actually holding. So it's holding a large amount of resources, so it will, P1 will release 45 more, right? I mean, 15 you already have, but 45 more, okay. And with the 60, I think you can satisfy anyone's future need. So the thing here is that this is the future need, which is the maximum need. Now the deadlock, the real deadlock, will depend on whether really P1 needs 25 or not. If let's suppose, what if, consider the worst to worst nightmare, okay? In that case, all of these processes are asking exactly about the future need, okay? This could be the overestimate. That's the thing, okay? If, because see, whenever process is getting submitted, you don't know the future, okay? I mean, that the future is determined by the runtime. Future will be determined. Let's suppose there are like conditions like if else, if x is greater than 2, then you need, let's suppose, these many resources. If x is less than 2, then you need these many resources. I mean, the program could be as complex as you can even not think, okay? So the future will be determined by the actual program. So that is why you don't know whether this is the program will be actually asking for this, or this is just overestimate. If this is overestimate, then there may not be any deadlock. So unsafe state is basically just telling, in worst case, if process actually ask, if all the process actually ask for exactly the future need, in that case the system will be in the deadlock. But what if they are asking for less? If they are asking for the less, then system may go to the smooth process, and there may not be the deadlock, right? So that's why unsafe state is not deadlock, it is may or may not be the deadlock. I hope now it is crystal clear that why we are saying that unsafe state may lead to deadlock or may not lead to deadlock. It depends on the future actual need, okay? Not just future need, it will depend on the actual need of the process. So it is clear to everyone that what is this unsafe state and how it is related to deadlock, because some students just remember. If you also just remember, instead of learning the concept, if you also remember, then just comment it out, because many students just remember that, okay, future need means, oh sorry, unsafe state means may or may not be deadlock. But why that is the case, they might not be able to answer this very perfectly. Let's suppose someone ask in interview, then they might get stuck. So now I hope this is more clear, okay? Great. Now let's just move to the next question. The next question was also bit interesting, and this question was basically related to something called priority inversion. I mean, there is one famous problem that is called priority inversion. And the reason why I put this question, because Gate sometimes asks the famous things directly. Okay, Gate has I am not sure. I think most probably Gate has not directly ask this problem in any question, but yes, Gate may ask it, because this is the popular problem. So let me just explain you that what they are asking in the question. They are saying that initially, let's suppose, this is given to you. They are saying that you have two processes in the system. Let's suppose PH or PL. PH is high priority process, high priority process, and PL is low priority process. Okay. Now, they are saying that if you have these two processes, if you have this critical section, then will you get onto the deadlock or will you not get into the deadlock? Depend, I mean, let's suppose you are having two schedulers also. One of the scheduler is obviously the priority scheduler and another one is round robin scheduler. Okay, so in the question they are saying there are two schedulers, priority and round robin scheduler. Okay, there are two schedulers which are possible. With which scheduler, okay, the deadlock is possible? That's what they are eventually asking. So as you know that how test and set work. So initially let's suppose t is 0. Okay, how test and set work, it will say that it will return the old value and it will set the t to 1, right? So basically if initially t is 0, then any process can get enter, and then finally t value will be 1. Now interestingly here they are saying that it is possible that system initially start with only one of the process in the ready state while the other process become ready at some later point in time. Both process need not to be at the ready at the start, which means they are saying that it is possible in the system. Let's suppose there is only low priority process and only high or only high priority process. I mean, may not be both the processes coming at the same time. Okay, now let's just assume that only PL is there. Okay, only low priority process is there in system. Okay, let's just assume that only PL is there in system. Now what will happen? PL will come and it will set this T to 1 and it will get into this critical section, right? Now once the PL is in the critical section, let's suppose PL is here. At that point in time, suppose suddenly PH comes and ready, okay, in the ready state. So let's suppose PL is here and PH comes in system, obviously first in ready state, right? Now, if it is a priority scheduler will say, since I have the high priority process with me, let me just run it. Okay. So it was running PL, but PL will get preempted at this moment. See here, this is very interesting. At this moment, PL, which was a low priority process, it will get preempted. Okay. So low priority process will get preempted because it is a priority scheduler. Priority scheduler will always prioritize the high priority process. And now PH will try to enter in the critical section. But since T is already 1, it will not get into the critical section, right? PH will be stuck in here. PH will stuck here in the while loop. Stuck in while loop, right? But since it is a priority scheduler, it cannot run the low priority process, right? It will give complete CPU to PH only. And PH is just wasting the time. PH will not get into the critical section. It is just stuck in the while loop. Because PL has set this T equal to 1 and PL got preempted and there is no one who can unset or who can just reset this T equal to 0. So that's why PH will just wait here because T is 1 and PH will keep on waiting. So that's why the system will go in the deadlock. Okay, this is very interesting. See, PL has set T equal to 1, but now PL got preempted and there is no one. Let's suppose there are only two processes that are there. Okay, and there is no one who can reset this T equal to 0 because PL can only reset, right? I mean, PL has to come out and then can only reset this. Then since it is a priority scheduler, that's why PH got the priority and PL got preempted. So high priority process is trying to acquire the log, which it cannot acquire because it has already been acquired by low priority process. And since low priority process cannot be scheduled again because it is a priority scheduler, so it will only schedule the high priority process until unless it is finished. So that's why PH will stuck and system will be in the deadlock, right? But what if consider the same case, but what if it is a round robin scheduling? In case of round robin scheduling, what will happen? Okay, consider the same case, right? I mean, PL got preempted, PH came. Consider the same case. But will it get stuck forever? It will get stuck for sure. But there will be some time. After some time, the quanta is over, and then PL will get scheduled again. And the moment PL gets scheduled again, it will finish the execution based on the quanta, and it will just set or reset this T equal to 0. And then the moment PH comes again, it will say that okay, now let me enter. So with the round robin, since PL is getting the progress and it will eventually reset the T equal to 0. So with the round robin, there is not a problem, right? With the round robin, there is not a problem. But with the priority scheduler, sorry, this high priority process, which is PH, is this will get stuck forever in this while loop. So I hope this is clear to everyone. Okay. See, the idea is simple that in the round robin, since PL will get some time and it will eventually get out of the critical section, and then PH will get its own quanta to enter into the critical section, right? Now consider a case. So basically here you can just mark the question where under the priority scheduler deadlock is possible, and under round robin deadlock cannot occur. So A and C are the answers. Answer A and C. I hope you understood. But here I just want to tell you little more. Okay. Here I just want to tell you little more. Consider the case of round robin itself, and let's just talk about one interesting case. See, here they are saying each processes follow this pattern: entry, critical section, exit exactly once, which means there is no while one. If you notice, there is no while one here. Generally in some questions we write while one, right? I mean, it can keep on entering, so there is no while one here. Okay. So this is like simple, a simple entry exit. There is no repetition of the critical section. Each process tries to enter in the critical section only once. Okay, so let's just consider variation of this question where you have while one also. Okay, which means you have while one. Okay, in that case, what will happen? Okay, see, in case of priority scheduler, nothing will change. I mean, PH will get stuck and PL is here. So in case of priority scheduler, nothing will change. But let's just take round robin scheduler. Okay, in round robin scheduler, will anything change? See, if it is a while loop, in that case, PH will get stuck, PL is here, but PL, once the PL get quantum, it will come out of the critical section, but it is possible that it is again acquiring the lock, right? Because since t equal to 0, and then it will again set t to be 1. And then it is again in the critical section. So the moment PH is coming, before that it is always, exiting and entering. Okay, suppose the quanta is large enough that it is exiting and entering. Okay, the moment the PH turns come, it is always in the critical section, right? Because it is a repetition. So in that case, even in round robin, there will be. I mean, you cannot say deadlock because the system is not in the stuck, because there is some progress is happening, because PL is getting progress at least, right? I mean, PL is executing on its quanta, but yes, PH got stuck. So you can say in that case, there is a starvation. So PH will starve, right? So starvation is there. Deadlock is not there. Okay, deadlock is not there in round robin. The reason is that for the deadlock nothing should progress, but here PL is getting progress, right? So you can say deadlock is not there. System is not deadlock, right? So better line to write: system is not in deadlock. System means the combined process, both the process is not in deadlock. But if it is while one, okay, if it is while one, then starvation is there. Okay, in round robin starvation is possible. Isn't it interesting? So bounded waiting is not there, because starvation is there. So bounded waiting is not there. But yeah, like consideration of this variation is also very interesting. Okay, so I hope like you have little bit understood what I'm trying to say. Okay, let me know if there is any doubt here at this point. You can always comment and let us know if there is any doubt. Now let's just move to the next question. Let's just see the next question. Okay, so this question, to be honest, was easy only. It was not that tough. Okay, so this question was related to TCP, where we are talking about few things in the TCP, right? So let's just see. Let's just see this question. Okay. So here in this question, by the way, this information is there, this information is there, this information is there, and there are like two, three information which was not useful for this question. You will get to know why I'm saying so. Okay, so there are like three information I can say which are not useful, but still I gave it because this I have taken from one gate PYQ, and in that gate PYQ also, almost same question they have asked. Okay, almost same question they have asked. So these three information will not be useful for this question, but let's just see why I'm saying so. Okay. So just read out this question, what they are saying. Let's suppose TCP is operating with some congestion window, 4 KB, and receiver is advertising on the receiver window of 8 KB. At this moment, sender has transmitted the data up to 20,000. Okay. So they are saying sender has transmitted the data up to 20,000. I mean, this is transmitted. Okay. Sent. Sent. The receiver acknowledge all the bytes till 16,000. So basically this is sent, that I agree, but receiver is acknowledging. Okay. So all the bytes till here. So you can say these are even acknowledged. Okay. This is sent and acknowledged. Okay. So basically sent could be divided into two parts. This is acknowledged, I mean sent and acknowledged. This is not yet acknowledged, right? Not yet acked. Based on this information, which of the following byte numbers are guaranteed to have already been sent by the sender? So they are asking, based on this information, like which of the following byte numbers are guaranteed to have already been sent by the sender. So basically they are asking that which of this has already been sent. Okay. So obviously 16,200 is this sent? Yes, this is sent. 18,000 is also sent. Is 20,001 is sent? No, because they are saying that okay, only 20,000 till 20,000 has been sent. So obviously, like this is sent, this is sent. I mean, this is not sent, this is not sent, right? I mean, you don't need this information. You don't need this information to solve this question. You neither need this information, right? So yes, so A and B are the answers, which means yes, 16,200 is sent, 18,000 is also sent, right? Now suppose someone asks you, this will be interesting. Someone asks you, is the byte number 10,000 has been sent or not? What will be your answer? See, firstly, the answer of this question, I think, let me just check the answer. Should be AB, right? So basically, till this point, as I told you also, okay. So till this point, you have sent, right? Till this point, you have sent. Till this point, sent. But till this point, you have even acknowledged, right? So these are SEK'd. Okay, so basically, this is 16,000. Till the 16,000, you have acknowledged. Until 20,000, you have sent. But let's suppose someone asks you that have you sent this 14,000? Okay, let's suppose this is 14,000, byte number 14,000. Have you sent it? What is your answer? In TCP, you start with some initial sequence number. So you don't know whether the initial sequence number is less than 40,000 or greater than 40,000. Maybe the initial sequence number is 15,000, right? So you don't know whether the 14,000 has been sent or not. Okay, it doesn't start with zero. It need not to start with zero basically, right? So that's why you will say, if someone asks me, see, if the in the option, if the one of the option is, let's suppose 14,000, right? 14,000, which means they are asking whether the 14,000 has been sent or not. Then answer is you don't know, right? If the yeah if the question is about guaranteed to have already sent, then 14,000 is not the answer. Okay, because you don't know whether it has been sent or not. I mean, it depends on the initial sequence number. So see, this is guaranteed, but this will depend on initial sequence number. Intentionally I have not put this as an option, but this could be interesting option. Maybe I can modify this question later, and maybe I can just put one of the option like this. Okay, will depend on initial. Understood. Great. See, in gate also sometimes they ask these questions where they give some extra information which is not even needed. And I think this is almost the same replica of one of the gate question. I do not remember the year, but I will just put in the comment section whenever I find it. Okay. So it is exact replica of one of the gate question. Okay. Almost the same replica. Great. Now let's see this question. This question was again related to computer networks. So here they are asking about a functioning of DSCP, right? DSCP means Dynamic Host Control Protocol. It is one of the protocol to get the IP address. So this is the standard, protocol, and it follows the standard, obviously, rule, which is called DORA, DORA, okay, which means discovery, offer, request, and acknowledged. Okay, so DORA, I think, yeah. B is the correct answer here. I will just explain the detail, but yeah, B is the correct answer. Let me first, give you the answer, that DORA. Okay, this is the answer. So I've not written B, but yeah, so B is correct. Now let's just first explain this. What is this DORA? Okay, DORA process. So basically, whenever some client is there and then it doesn't have its own IP address, so it requests some DSCP server to get IP address. So it just first send something called as discovery message. Okay, so some discovery message sends, which is a broadcast message. It sends a broadcast message to all the servers. So there may be multiple servers. It sends to all the servers, and then the broadcast message. This is called discovery. Then one of the sorry, like whatever server, okay, whatever server are there with the IP address, they will reply. Okay, so let's suppose this server is replying, maybe the other server is also replying. So there could be multiple servers which are replying. Okay, let's suppose this server is replying and saying that, okay, I can help you. Okay, it's like that. See, this is, let's suppose, client, and let's just take the case of multiple servers even. Okay, this is, let's suppose, server. This is, let's suppose, another server. Okay. So client is first asking, can you help me? Basically, give me IP address. Client is asking to everyone, give me IP. Okay. This is called discovery. Okay. It is just discovering. Discovery. It is a standard name. That's why I have asked this question, because gate can anytime ask some of these questions also. Okay, so it's good to have, the questions which you don't know in the test series, right? Not in the gate obviously, but in the test series, good to have the questions which you don't know. Probably gate asks at least, like, I mean, there's a huge benefit. Not at least, like, there is a huge benefit, right? So sometimes we ask some questions which you might not be knowing. Or obviously in Go classes course we have taught everything. We have taught this also. We have taught Dora process. We have taught everything. But maybe you might have forgotten, right? Okay. So it is sending discovery message to everyone. Then server, whichever server has the IP address, they say, I can help you. Okay, which means offer. This is called offer. Okay, this is called offer. Offer message. It can also offer, right? Okay. Now it will accept, the client will accept one of the offer, and it will just request. Okay, now it is saying that, okay, I'm accepting this offer. It will just request, okay, to, let's suppose, server one. Okay, request to server one that give me IP. Okay, I mean, I want to take your offer, but it will also, broadcast it. It will basically send this to everyone. Request to server one. Okay, even though this is server 2, but it will send this message to server 2 also. So the server 2 also get to know, okay, the request has been made to server 1, not to me. Okay. Then obviously the server 1 will only reply. It will request that, okay, see, initially it is saying I can help. Then it is requesting, okay, please help me. Then it will say that, okay, here you go, which means it will give the IP. This is your IP, right? So it will say, here you go, which means this is called acknowledge. Okay. ACK message, that here you go. Understood? So basically, this is like four step process: broadcast, and then discovery, offer, then request, and then ACK. Okay, you have got that IP address, something like this. Okay. Now, like, probably you might not know this, but still, I'm just telling you that these messages, whatever client send, okay, are always a broadcast message. I mean, this is a broadcast message. This is a broadcast message. But whatever server sends, it could be unicast or it could be broadcast. Okay, it depends on the implementation. Okay, so these messages need not to be broadcast. All messages could be broadcast, but whatever the server is sending could be unicast also. It depends on the implementation. So you do not need to know this detail, but still I'm telling you that DSCP offer, which is server is sending, whatever server sends, okay, this message can be unicast or broadcast. This message can be unicast or broadcast. Okay, whatever server sends, it could be unicast or it could be broadcast. Anyway, don't worry about it. This is not much important. The process is more important, because they might not ask these implementation detail things, right? Because if something is very much implementation detail, then they probably won't be asking. Okay. I hope you understood this. This is, not very tough question. At the same time, it is just, the process that you know. If you don't know, then probably you won't be able to solve. If you know, then this like 30 seconds of the question. Okay. Let's solve this question. In this question, they are asking very simple thing. This is, not tough question. This is a simple question only. In this question, they are just saying that There is an international airport which is Pittsburgh, and then I've just arrived at Pittsburgh International Airport, and I have forgotten where I have parked my car. There are n cars in the parking lot. I decided look for my car with a simple serial search, examining one by one each and every car in the lot. This algorithm could be analyzed by considering the best, average, and worst case. So basically, they are saying there are different cars are there, and I want to search for my car in the serial. Okay. So obviously, like this is just a linear search, and they are asking just about the linear search. But the question is more interesting because they are testing your knowledge related to the asymptotic notations, right? So this is big omega, which means this is like this. This is big O. This is big O. This is theta. Okay. In worst case, the algorithm is, see, some of the students have even made the mistake, instead of I mean treating this as a big omega, they have treated it as like big O. Okay, so that's why we have put this in English names, not the mathematical notations, because gate can trick you anytime anywhere, right? So we need to keep all the possibilities open. Okay, in the worst case, the algorithm is saying it will be taking big omega of 1, which means big omega means that that greater than or equal to 1. In the worst case, you will be taking greater than or equal to 1. Yes, that's true. In the best case, you will be taking less than or equal to log n. Yes, in the best case, you will be taking less than or equal to log n. Actually, you will be taking 1 only, so that's why this is true. In the best case, less than or equal to n. Yes, this is true. In the worst case, exactly equal to n square. Theta of n square means exactly equal to n square. I mean, obviously, I'm not worrying about the constant. So in the worst case, will you be taking exactly equal to n square? No, this is wrong. See, this could have been correct. In the worst case, it will take exactly n. So if this is big theta of n in the worst case, then this is the correct option. Okay, but because of n square, it is wrong. And some of the students are having bit of the confusion, or I can say they are not very clear about one thing, which is that they think that for the worst case we cannot use big theta, or we cannot use big omega, or like this, right? For the worst case we always use big O, something like this. But no, that's not true. Like, I mean, for the same question, if we have big theta of n, then this is true. In the worst case, if you have big omega, then this is also true. I mean, they just think that these three cases, which means worst case, worst case, best case, average case, right? They just think that these three cases are related with, like this. I mean, for the worst case we always use big O, for the best case we always use big omega, for the average case we always use theta. Okay, this is completely a wrong thing. I mean, this is a misconception. For any case you can anything. For worst case you can use this, you can use this. For worst case also you can use this. I mean, for any case you can use any of this notation. These notations and these cases are not directly related. Okay, so this is a misconception that it is one to one mapping. Okay, so one to one mapping is misconception. And we have talked about it in the course, so I'm not going too much detail, but I hope you understood with this help of the question that in the worst case also we can use big theta, we can use big omega, and so on. Okay, great. So ABC are the correct answers here. So ABC are the answers, right? Now let's just move to the next question. This question was related to minimum spanning tree, and it was one of my favorite question. This was not tough question, to be honest. It was just interesting question, I can say. It was not tough. It was just easy, or I can say interesting. So let's just solve this question. Okay. This was based on two properties. One is called cut property, another one is called cycle property. So they're asking about the edges. So basically, in the question they are saying that this question mark means there could be some graph here. This question mark means there could be some graph here. So each edge marked with a question mark connects to some unseen vertex. Okay, the two edges marked with a question mark are the only edges that connect the shown portion to the rest of the graph. So basically, there is no other extra edges. I mean, this A is not connected to the rest of the graph. This B is connected to some vertex. C is connected to some vertex. There could be some edges in between them, and that's okay. But yeah, some remainder of the graph, some unknown remainder is there. Some unknown remainder is there. Okay, I mean, there is no other information that you should be assuming about this graph. Now they are saying that for each of the edge, we need to determine whether this edge will appear never, always, or sometimes in the minimum spanning tree for the full graph. Interestingly, they have also given the definition of sometimes here. Here, sometimes means that edges appear in the minimum spanning tree for some valid completion of the unseen part of the graph and does not appear for some other value, other valid completions. So basically, they are saying sometimes means sometimes it should appear and sometimes it should not appear. Okay, so sometimes here you have to tick sometimes only when there is a case where sometimes that edge might appear and sometimes that edge might not appear. Okay, in that case only you should be taking this sometimes. So let me just solve this question for every edge. Okay, so let's just talk about all the edges. AB is one of the edge, AC is another edge, I think BC is another edge, B question mark is another edge, and C question mark is another edge. So I think there are like 5 edges. We can talk about those 5 edges. Okay, will this AB be part of minimum spanning tree? Never, always, sometimes. What do you think? See, since it is a cut, and here in the cut it is the minimum edge, so that's why yes, yes, always. I mean there is no confusion. Okay, this AB is always, because this is a cut, and here it is a minimum always, right? What about AC? AC. Since, see, this is interesting. This AC is a part of a cycle, and this is the maximum age of the cycle. So it will never appear. Okay, never appear. Because why? Because of cycle property. Cycle property says that maximum weighted age in the cycle, if it is unique, okay, then it will never appear. Right? So because of cycle property. Okay, this is the maximum edge, so that's why it will never appear. This is called cut property. So it is always because of the cut property. Okay. What about BC? Yeah, this is interesting. What about BC? Think about it. Okay, before BC, maybe let's just solve for others. What about B question mark? See, this edge. See, if you see here, if you cut it, right? If you cut it, this is always minimum, right? This is like interesting, just a eyesight observation. I can say, okay, this question could have been solved. This particular, could have been solved just by looking at this cut. Okay, if you look at this cut, this BC is all, this B question mark is always minimum. So that's why this will always be included. Okay, this will always be included. Actually, some of the students got confused in B question mark. They are not very much sure whether it is always or sometimes, or like, I mean, what was the case, but it is always be included. The reason is that because of this cut. Okay, and B question mark always was not even in the options. Okay, intentionally I have not put this in the options. B question mark never and B question mark sometimes is actually not the answer. Okay, why sometimes is not the answer? Because it is always, and sometimes definition in this question says that sometimes it should and sometimes it should not. Okay, but there is no case where it should not, so that's why this sometimes is not the answer. Okay, because always is that, so basically no case is a subset of other case, which means it is not the case that, okay, if the answer is always, then answer is sometimes also. No, always, sometimes, and never, these are the three distinguished cases for this question. Okay, so basically the sometimes is not the answer, never is not the answer. So this, I mean, for B question mark. Yeah, let's just solve for other edges. What about C question mark? I think it will depend. If this is just suppose just one vertex and this is the only thing which is connecting, then yes, sometimes yes. If let's suppose this D is also connected here. Okay, let's suppose this is some vertex and D is also connected here, then probably not, right? I mean, it will depend on the valid completion. So sometimes you can say it is sometimes, right? So so AB always, yes, this is true. C question mark sometimes, this is true. So A and D are the answers here. A and D are the answers. We have not asked for BC and we have not asked for AC, right? So let's just see, I mean, these are not asked in question, but still we are solving it. Okay. So let me just write it here that this is not asked in question. But it's easy only. But let's just write not asked. What about BC? I think it is easy again to see using the cut property. If you see this cut, right? If you see this cut around the C, right? Around the C, basically, if you see this cut, maybe you can see this cut. If you see this cut, then this is the minimum, right? This is minimum. So that's why it is always. So you can say this is always because of cut property. This B question mark is always because of the cut property. C question mark is sometimes because of, oh, again, the cut property, right? I mean, sometimes the cut property may apply, sometimes the cut property will not be applicable depending on the valid completion, right? So this is the answer for this question. I hope you understood. Now let's just move to the next question. Let me know if there is any doubt in this question. If there is any doubt, you can always comment and let us know. So again, this question was related to dynamic programming. Okay, this question was related to dynamic programming, and this was a simple question, which is just asking to write some formulation. Okay, so they are saying that for a positive integer x, dx j denote the number of ways to write x as summation of the numbers chosen from this. So basically, they are saying that from a1 to aj, if you are basically writing a1 to aj, then dxj denote the number of ways you can write summation of x using a1 to aj. For example, if x is 5 and the numbers are basically 1, 2, 3, 4, let's suppose these are the numbers, okay, till a4, okay, then using these four numbers, can you write 5? Yes, you can write 2 plus 3, you can write 1 plus 4 like this. So there are two ways, right? So D, 5, 4 are two ways, right? So what about DXJ? DXJ means that using this A1 to AJ, right? Using this A1 to AJ, can you write X as summation? So in these questions, there is DP question. It will always be the recurrence will always be written in based on the two cases, whether you are taken this AJ is taken into the summation or not taken, right? So just see that which is the correct. So if you are taking, then how many number of possible ways? If you're not taking, then how many number of possible ways, right? This is the question that you are asking. If you're taking, then d, then remaining sum will be x minus aj, right? And using j minus 1. If you're taking, right, taken, in case of taken, this will the recurrence. If you're not taking, in that case the remaining sum will be based on aj minus 1 obviously, but the remaining sum will be x only, right? If you're not taking. So number of ways using taken, number of ways using not taken. It is possible that one of them could be zero. I mean, if you're taking, let's suppose it is a so big number that x minus age is even negative number, right? So base case will handle these things. It doesn't vary. But yeah, these are the total number of ways. If you're taking, then it will be j. I mean, j minus will be one will be anyway in both the cases. But if you're taking, then x minus age will also be there. So what is the answer? Um, Minus is not the answer. Yeah, I think B is the correct answer, right? J minus 1 will be there. If you're taking, then X minus AJ, right? B is the correct answer. Okay. So it was easy question, but at the same time, like Gate just asked these questions, and I hope if you are good with the dynamic programming, then you can solve this question. And if you were not able to solve, then still you have learned something, right? So it's good in both ways. It is good. It is just a practice. Great. So basically, always take or do not take, right? I mean, take or do not take. These are the always two cases in case of dynamic programming. I mean, consider all the cases. There could be multiple cases. Like here, I'm saying take or do not take. Maybe some other. Uh, see, it is like a binary decision: take or do not take. Maybe sometimes I do not remember anything where you may have to decide between three possibilities. Okay, it is possible. You may have to decide between three possibilities. So you have to sum up all the possibilities, or based on the question, maybe you have to multiply all the possibilities and so on. Okay. Now let's see this question. In this question, they are saying that this particular array is almost max heap, but you just have to basically swap number of elements, a minimum number of elements to make it max heap. So what you can do, I mean, you can just quickly check that what are the minimum number swaps that are needed to make it max heap. So you can just make the tree out of it, complete binary tree, right? So 100 will be here, and then 75, then 90. Till now it is a max heap. Okay, maybe let me just draw all the um, nodes, 76, then 15, then 9, then 8, then 14, and then 13, right? Okay, this is not a maxi because of this. What about if I swap these? I think if I swap this will be 80 and everything here will be below this. Yeah, I think I can swap this, right? And they're not asking about the heap operation, they're just asking about the array swap. So maybe 75 and 80 we can swap. Okay, 75 and 80 we can swap. So number of swap operations are needed are just one. Okay, great. Now let's move to this question. This question was related to hashing and a bit related to probability also. Hashing and probability mixed kind of question. Gate also asks these questions. So let's solve. Okay, let's see that what will the answer of this question. So what they are saying, suppose a hash table of m slots and only one of those slots containing single element with k. So basically they are saying there are m slots, maybe 0 to m minus 1 or doesn't matter. So basically there are m slots are here and one of the slot is containing the key k, right? And the remaining slots are empty. Say we search in this table for x various other keys, none of which are equal to k. So basically we are searching for, let's suppose, some x number of keys and none of this are equal to k. I mean maybe 5, maybe 10. Let's suppose k is 7. Then we are never searching for 7, something like this, right? And we are having x number of searches. Assuming simple uniform hashing, which means that everyone will be getting the equal chance. I mean, this x, okay, this, I mean, let's suppose I'm searching for 7, or let's suppose I'm searching for 10, then 10 will get, will equal probability to map any of this, okay? Simple uniform hashing means this. What is the probability that at least one of these search probes the slot containing k, which means that you are asking for k. What is the probability that you are asking for? The question is this. See, the probability, at least one of this, right? They're asking. The probability to ask for k is 1 by m, right? I mean, probability to ask for this slot is 1 by m, right? Probability to ask for this slot is 1 by m. Is this okay to everyone? Probability to not ask for this slot is 1 minus 1 by m, right? Probability that none of this x searches ask for this slot is this, right? So basically you can say the probability, this is the probability that none of this x none of this x searches ask means probe, okay? Probe ask for this slot. Okay, so it's like basically it's like the none of this, which means it's kind of, you can say, the probability in mathematical term, it is like equal to 0, okay? I mean, none of this means number of props that are going to this is equal to 0, right? Number of props, or maybe less than, let me write less than 1, just because it is integer, so it doesn't matter. Less than 1 means equal to 0 only, but just for the sake of explanation, number of the props, so here you can write number of the props going to this slot, number of props going, sorry, number of props going to this slot. And what is this probability? 1 minus 1 upon m power x. See what I'm saying, that you have one of the slot which is containing k. I'm just asking you what is the probability that none of, out of x props, right? Out of x searches, so none of the probe is going to, let me write this slot, okay? So what is the probability that none is going to this slot? The probability to go to this slot is 1 by m. Probability to not go to this slot is 1 minus 1 by m. Probability that none of the slot, I mean all you take all x props, none of these props go to this slot is 1 minus 1 upon m power x. But this is not they are asking. They are asking that what is the probability that at least one is going. Okay, so it is the probability, you can say in mathematical term, probability that equal to zero. I mean none of the, I mean you can say the number of props are equal to zero. Okay, going here, number of props going here is equal to zero. Number of props going to this slot equal to zero is this probability, right? Which is 1 minus 1 upon m power x, right? I mean that's not being asked, but we will just come to what is being asked. Okay, they are basically asking, they're asking that at least one is going to this slot. So basically equal to zero is okay. I mean you can write equal to zero, but instead of that let me also write less than one. Less than one, I mean less than one is equal to zero only. But if I do, if they're asking the same thing, they're asking, but they're asking greater than equal to one, at least one is going. Okay, I mean the same thing they're asking now, the number of props going to this slot should be at least one, which means greater than equal to one. Okay, so what is this probability? Tell me. It will be 1 minus this probability, right? I think I should not have given this question as 1 mark. Okay, this could be the 2 mark question, but that's fine. Is this fine to everyone? Tell me. So which means it is at least one is going here. It is 1 upon m power x. Okay. So this was quite interesting, little tough also. I can say like this was tough question. Okay. So B is the answer, but yeah, that was a tough question. Great. So let's see the answer. Yeah, 1 minus 1 upon power x. Okay. Now let's just solve other questions also. So let's solve this question. This question was related to first in first out page replacement policy of operating systems, right? So they are saying consider system with 4 page frames A, B, and then this is the axis pattern, right? A, B, A, C, like this, right? And FIFO is being applied, then they are asking for number of page faults. Okay. This is not a tough question. I think you can solve this question easily. Let me try solving this. So since you have first in first out, which means, and you have 4 slots only, so you can, I mean just you can make a queue, which is okay. I mean basically I'm making a queue because it is first in first out, right? And you have 4 slots. I mean queue maximum capacity could be 4. So first A is coming, this is obviously a page fault. For the page fault, I mean this is kind of compulsory page fault. For the page fault I'm just marking, okay, this. Then B is coming, this will be a page fault, right? So I'm marking this also. Then A is coming, this is not a page fault. Then C is coming, this is the coming first time, it is a page fault. Then D is coming, this is also page fault. So till now 4 page faults. Then E is coming. If E comes, then A has to push out, right? Then E is coming, then A is no more here, and this is a page fault. F is coming, then B is no more here, and this is a page fault. A is coming, then C is no more here, okay, and then this is a page fault. And then B is coming, okay, then B is coming, then D is no more here. So basically currently you have E, F, A, B, right? So this is also page fault. If C is coming, then E is no more here, then this is also page fault. If F is coming, this is not a page fault, okay, but this is already there. A is coming, then this is also not a page fault because it is already there. E is coming, then this will be a page fault, right? And F is coming, then this is also page fault. Okay. So how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Right? So 11 page faults. Right? It is easy question because they have asked for FIFO. 11 page faults. I hope you understood. Great. Now let's just move to the next question. It was easy question. It was related to calculus, which was basically related to, you can say, L'Hopital rule. Okay. So this question was, they are asking for the limit this. So what you can do, this is basically, let me write on the next page probably. They're asking for this limit, and they've also given f dash x equal to x minus fx by 2. They've also given something, and f1 is 2. Okay, so they've given that this is the relation, F1 also they have given, which is 2. Okay, so if you put 1 here, you will get to know this is 2 minus 2 and 1 minus 1 whole square, which is 0.0 form. If it is 0.0 form, you can apply the L'Hopital rule, which means you can differentiate both numerator and denominator. So if you differentiate this numerator, it will be f dash x minus 0 divided by this is 2x minus 1, right? Now if you put 1, then f dash 1 is basically 1 minus 2 by 2, which is 1 minus 1, which is 0. Okay. Now if you put 1, then it is f dash 1, which is actually 0 divided by 1 minus 1, which is again 0, right? So yeah, so basically it is again coming out to be 0 by 0 form. So you can differentiate again. So if you differentiate again, it will be f double dash x divided by this is 2 as it is, and then this is 1, right? 2 into 1. So you can just write 2 here. Now if you put 1, so f double dash 1 means you need to differentiate and calculate f double dash x, which is 1 minus f dash x divided by 2, and then f double dash 1 means 1 minus f dash 1 divided by 2. F dash 1 is already, you can calculate, it is I think 0, right? So 1. Okay, so it is 1 by 2. So ultimately 1 by 2 is the answer, because f double dash 1 is 1, so 1 by 2 is the answer. Okay, so yeah, D is the correct answer here. Great. So it was not tough question, it was a doable question, I think, right? Now let's solve this question. This question was related to struct and was related to C programming. So what they are saying that let's just consider a pointer, okay, which is pointing to a struct. Okay, let's suppose this is one struct and S is actually pointing to the struct. Then they're asking that what does this star S dot data mean? Okay. See, star S means struct itself. Like if it is pointer to integer, then star P is basically the integer itself. So that's why star S is the struct itself. And then the way we access, let's suppose one of the member is data. The way we access any member of the struct is basically the name of the struct dot data. Okay. Name of the struct, basically you define struct, right? Struct, let's suppose some struct is there, then you write struct name, okay, maybe capital A or something, right? So you define some struct and then you write capital A B, something like this. So this is the name of the struct, but you can also ask some pointer struct capital A star or something like this, right? I mean, you can ask some pointer to point it. So S is a pointer, but using the struct name, if you want to access any member, then you do like this, right? Star s dot data. But using a pointer, they are saying that if you want to access directly, then this is just well known notation that using the pointer, if you want to point directly, then you can use s data. Okay, s data. I mean, using a pointer if you want to access the member of the struct directly. Okay. So S data is correct answer. But why not this? Why not this? See, this is even invalid. Like you don't have, like, this is not a struct. This is a pointer to a struct, so you can't use dot directly. Okay, you can't use dot directly. But what about this? What about B? See, see, in the cases like dot and star, these all have the same precedence. So that's why you always, like as I told you, this is since left to right associativity. So you always go to the right. Okay, I mean, you don't go to the left first. You go to the right and then you put the bracket. So basically here in this case, this dot will be evaluated first. Okay, since dot is getting evaluated first, that's why this is wrong. If star, by some chance, let's suppose there is some rule that star is getting evaluated first, then these two are same, isn't it? These two are same. But here in this case, dot will get evaluated first, so that's why this is wrong. Okay. So how to remember whether dot will get evaluated first or star will get evaluated first? You always go, or pick your main variable and always go to the right. Okay, whichever is coming first, it will get evaluated first. This is a thumb rule in C programming. So that's why this B is wrong, because this is same as s dot data, and then s dot data is invalid actually. But yeah, this is same as s dot data star, which is wrong. Okay. Now let's solve this question. So this question have turned out to be interesting question. The reason will be obvious to you. So here in this question, I'm just asking for the sum. But the interesting part is that I'm asking for the sum, but I is unsigned integer. and they are saying I is greater than or equal to 0. I mean, they're decrementing I from 5 to, it will be 4 and so on, but they're decrementing I, that's sure. But since it is unsigned integer, it will become 0, but it will never become negative. Okay, so it will become minus 1, but minus 1 is too large number. I mean, in unsigned integer, minus 1 is too large number. I mean, unsigned integers are never negative. So this condition, this is always true for any unsigned integer. Okay, this is always true for any unsigned integer. So that's why it is infinite loop. Okay, it is infinite loop. Hence, none of the above. Okay, intentionally I have not written infinite loop as an option. Okay, just to not give you the hint. But yeah, this D is the answer, as it is infinite loop. Okay. This question was more like, this question is there just to tell you that you should be more aware, or you should be more focused while you are reading the questions. Some people like this question. Maybe you may not like this question. That is okay. But it may ask, right? I mean, you should be focusing that what is written. So, so just see, take these questions just as a practice question. So it is there just to let you know the importance of unsigned. Okay. Yeah. So let's solve this question. This question was interesting question, because here again this was C programming related question, and in this question they are asking about what is the relationship between tilde of x and this x minus 1 and so on. See, this tilde of x is actually one's complement, which means this tilde of x is one's complement, right? And minus x is basically, we write minus x in the form of 2's complement. So basically, minus x will be, the negative number will be one's complement tilde x plus 1. Okay, mathematically it is always true. You can take any number of your wish. Okay, the way we represent let's suppose you can take minus 5. Okay, if let's suppose x is 5, then try to represent minus 5 in 2's complement, and take the 1's complement plus 1. It will be always true, as you know, right? So basically this thing always holds. Now they are asking just minus 1 both side. Okay, if you do minus 1 both side, then it will be tilde of x only. So this is always true, but yeah, this is tilde of x only. Interesting question, isn't it? Simple question. Just you should be knowing that minus x is just 1's complement plus 1, and this is actually true. Okay, you can even write the C program where what you can do, you can use some condition. If tilde of, sorry, minus x equal tilde of x plus 1, and then you can even write the while x equal to minus 100 to plus 100. Okay, something like this, right? I mean, you can just it will just print true for everything. Okay, because it is actually true for every number. Positive, negative doesn't matter, right? Great. Now let's just, yeah, B is the answer here. Now let's just move to the next question. So this question was a linear algebra question, and in this question they are asking that if this is determinant of a minus lambda I, which means these are the eigenvalues. Okay, determinant of a minus lambda I means lambda is the eigenvalue here. So which of this is true? So first you need to factor this. Let's just factor this. So basically you can see that from these two you can take lambda square common, and then this will be minus lambda plus 3. Okay, so maybe let me take minus lambda square common. So it will be plus lambda minus 3. Okay, I mean just taking minus also, plus lambda minus 3. Okay, this is lambda minus 3 as it is. So from here you can say minus lambda square plus 1 and lambda minus 3, right, equal to 0. So what are the eigenvalues? Lambda equal to 3 is eigenvalue, and lambda square equal to 1 is, which means lambda is equal to plus minus 1, right? So these three are eigenvalue, 3 plus minus 1. So what is the trace? Trace will be, I think, 3, because 3 plus 1 and minus 1. Okay, 3 plus 1 minus 1 is 3. So trace is 3. Determinant will be, I think, 3, right? Because 3 into plus 1 into minus 1 will be 3. So determinant is not minus 3, it is 3. The matrix A has the eigenvalues minus 3 and 1. Minus 3 is not the eigenvalue, right? 3 is the eigenvalue. So I think this is also wrong. Okay. So A is the correct answer. D is the correct answer. Sorry, if you take the determinant, then yeah, this is minus 3 only. Sorry about the mistake. So if you take the determinant, 3 into plus 1 and minus 1, it will be minus 3. So this is true, but yeah, minus 3 and 1, this is wrong. Okay. So 1 and 2 are the, these are the eigenvalues, and then determinant will be minus 3, trace is 3. And the last one was eigenvalues, right? Eigenvalues is not minus 3, it is 3. Here, yeah. So basically, we are just factoring. I've just also shown you that how to factor it. Okay. Let's solve this question. This question was related to again calculus, and there is one theorem in calculus called a mean value theorem. So this question related to this, because if you have solved gate PYQs of some MVT mean value theorem question, then they have the similar pattern, the greatest value of F0 or something like this, right? So let's just solve this. It was also, not very tough question. It was good question, but not easy at the same time. It was moderate kind of question. But before that, let me first tell you what is this mean value theorem. It says that if a function is continuous, okay, in a to b, the closed interval, and differentiable in the same interval, because the endpoint for the differentiability, the endpoint are not counted. So differentiable in AB, but the continuous in AB, there exists a C in this interval such that okay, there could be multiple C's, but at least one C they are saying. Okay, so there could be multiple C's here like this shown, such that the slope of AB, which is basically f minus fa upon b minus a, the slope of AB is this slope of this line, and f dash c means slope at this point C. Okay, are both are equal. Okay, so this is mean value theorem, and this is a diagram for this mean value theorem. I mean, you can see with the simple diagram just like this. Let's suppose these are the A and B. Okay. There could be just one C. It need not to be multiple C's, which means okay, which means this is the line which is passing through AB. This is f dash C. So both slopes are actually equal. Okay. So this is the question, but the condition is that AB must be closed. But here in the question they have given minus 3 and 4 are open intervals, right? So what you can do, you can take the closed interval. Instead of minus 1, you can take 0 and 3. I mean, minus 1 and 4 are here like this, right? And you can take the sub interval 0 3 here, and you can solve this question. So a equal to 0, b equal to 3. So fb, f3 minus fa upon 3 minus 0, it should be equal to some f dash c or f dash x, right? So f dash should be equal to f dash x. Okay, f3 is given to be 5, right? I mean, since see, we have taken a equal to 0 and b equal to 3, because f0 and f3 are actually involved in this question. So that's why we have taken. I mean, you can even take something like like some fractional value which is immediately here after minus 1, and some fractional value which is immediately before 4. Okay, I mean, we have taken 0 and 3 because 0 and 3 are involved in this question. Okay, so basically, let me show you the solution. So it will be 5 minus f0 and equal to f dash c. So here they are asking the greatest value of f0. So if you solve this, the greatest, I mean, f0 is always less than or equal to 8. So from here you can say the greatest value of f0 could be 8. Nice question, right? I mean, it was a good question. I'm not saying it was very good question, but I mean, good in the sense like it was nice to solve. It was moderate question. Okay, not too hard, not too easy. But yes, it is good to know about these questions, because GATE also asks these questions, right? Okay. Now let's solve this question. This question was related to something called as trees. I mean, in tree also they have taken they have taken, I think, the ternary tree. Okay, which means a tree can be having three children. Okay, exactly three children. So they are saying an internal node can have exactly three children. The height of the subtree rooted at any child can differ at most one. Okay. Now they are saying that th with the minimum number of nodes in the height h, which means in the height h. Okay, if this is h height, let's suppose th is the minimum number of nodes here, then how would you represent this th as a recursive relation? So basically, let's suppose this is height h, and this, I mean, total number of minimum number of nodes here are th. right? Since I want minimum, so that's why see, the height of this could be h minus 1, and one of this has to be h minus 1, another one could be h minus 2 or h minus 1, right? I mean, it could be h minus 1, could be h minus 2, could be h minus 3 also, but they are saying that the difference could be at most 1, so cannot be at h minus 3 in this case, but in general it could be h minus 3, h minus 4 or anything. Okay, so but the thing here is that if you want minimum number of nodes, so you want minimum height here, why you want more height? So the minimum height possible here is h minus 2, and at least one of them has to be h minus 1, but the other one, in the other one I have choice, right? In the other one, since the height difference could be at most 1, so the other one could be h minus 1 or h minus 2. But since I want minimum number of nodes, so I don't want more heights, I don't want lesser height, right? So that minimum number of nodes can come, so h minus 2 height will be there. So that's why if th is the minimum number of nodes here, then th minus 1 will be the minimum number of nodes here, because I want minimum everywhere. Then th minus 2 will be the minimum number of nodes here, and plus 1, right? So this recurrence relation could be written something like this. Suppose at the same time, okay, in some other question, let's suppose they ask for the maximum number of nodes. Okay, suppose they ask for the maximum number of nodes. Let's suppose they say sh or nh, or let's suppose th only. Th, let's suppose in this case this is maximum number of nodes in the height h. Suppose they define like this. Okay, sorry, this was 3, right? This was 3 children they have. So basically, you will be having one of them h minus 1, and for other two, you have the choices. So there could be h minus 2. Okay, so 2 into h minus 2 plus th h minus 1 plus 1. Okay. Now, maximum number of nodes. In that case, if you have 3, right? So this is a h height. So th is the maximum. So you want maximum everywhere. So here one of them should be h minus 1. For the other two also, for the other two also, take h minus 1. Why? Because you have the choice of h minus 1 or h minus 2. But since you want maximum, so take the maximum height, which is h minus 1. Okay. So maximum number of nodes in th could be 3 th minus 1 plus 1. Understood? I mean, this is h minus 1, h minus 1, h minus 1. So 3 at th minus 1. Th minus 1 is the maximum number of nodes and height h minus 1. So maximum number of nodes here, maximum number of nodes here, maximum number of nodes here. This t obviously is different from that t. So th is this. But currently 2 th minus 1, since they are asking for the minimum, so 2 th h minus 2 plus th minus 1 plus 1 is the answer. This is the answer, right? It was a good question, but if you have solved, AVL tree question, or if you have solved the previous test series, then this is approachable. Otherwise, that's fine. I mean, it was a new or different kind of question. It was a good question. Okay, so I think C is the answer. Great. So I hope you understood this question also. It was really a nice question. Now let's solve this question